I'll just start with logistics for the exam. So it will probably be about 10 to 12 questions. About one third will be the multiple choice conceptual style questions you'd see on quizzes. The rest will be calculation based, and those will be most similar to what's in that practice question packet. After that, it's probably more similar to what's in the notes, and then most similar to what's in the homework, just because the homework tends to be a little harder than what I give on exams. So, as far as what you can bring, you can have a cheat sheet. It can be one side of an 8.5 by 11 sheet of paper. You can put whatever you want on it. I do not care. I will take it up with the exam, but I'll give it back after I've graded them. I think that's about it. Oh, and there's a bonus question on every exam. They're always related to my dogs, either Toji, Mina, or both. 5 points, and it can be all sorts of things. So, as far as what to review, I'm going to go through each chapter real fast and kind of touch on what I tend to ask about from those chapters. So, for chapter 21, it is largely the conceptual style questions because the calculations end up being very similar to what you do in chapter 22. It's just we talk about fields instead of forces in chapter 22. So, 21, it'll be things like how does something acquire a positive or negative charge? And the answer is always through the transfer of electrons, not protons. Positive charge does not move, although we will pretend it does here soon when we talk about conventional current. It does not in reality. It's almost always the electrons that are moving between objects. So to get a negative charge, you have to add electrons. To get a positive charge, you have to remove them. And if I ask a related question of how many electrons do you need to add or remove, that's this right here. So I don't even really think of this as an equation so much as just it's stating the fact that you build up amounts of charge by just taking a pile of electrons and transferring it onto or off of the object. The number of electrons that you transfer in is the number you need to multiply by the charge of the electron to get the total charge. So if you want to solve for n, it's q over e, but that's just like saying if I've got a big pile of sand that, I don't know, has a mass of 100 kilograms and I can only pick up 1 kilogram handfuls at a time, how many handfuls is it going to take? It'll take 100. So think of it as math if you want, but it's kind of just observation. The next conceptual type thing is induction. So the thing with induction is that charge doesn't actually transfer between anything. It just shifts around within an object. And it's something that happens more readily for conductors than insulators because conductors have those really free valence electrons. So I could ask, like I hold a negatively charged object up to a neutral object. What happens? Your first instinct might be to say nothing because it's neutral, it's not charged, there's no force. But there can be induction where shifting of charge happens, even though overall it has no net charge. It can move around, and in this case, that would attract the can. And induction does always attract. The first calculation thing in 21 is Coulomb's law, and it would be questions probably along the lines of this one, where I'm just asking about directions of forces, possibly just a simple calculation with it like that, but I save the larger vector addition type questions for when we talk about fields in the next chapter. So the calculation for this chapter shouldn't be too bad. I'm going to save that for moving into 22. So for 22, this one can show up as I give you an electric field, maybe from a capacitor or something like that, and you have to tell me the force on an electron I put in there or a proton or something. And it's real easy because the idea is someone went in, did the dirty work of measuring the field for you. Now all you have to do is take the charge you've got and multiply it by that field. To get the direction, you just remember we defined fields in terms of positive charges. What would the force on them look like? So, as a result, positive charges feel a force in the direction of the field, negative charges feel a force opposite. If you put those two observations together, you can get both the strength of the force, and if it's an electron, it'll flow opposite the field. If it's a proton, it'll flow with the field. So, calculations like that, pretty straightforward for that piece. The big one for this chapter is this whole page right here, because it takes a whole page to do it. These questions can be 10 to 14 points. They can take up a big chunk of the points just because there's so many steps. It is probably one of the longer calculation problems that I could give, and it's the most messed up. Like, by and large, across every semester, no matter what level of the course I teach, this is the thing that I see the wildest answers for. And it's because if things go wrong at first, they never go right again. So this is where you need to be really careful about drawing your vectors. So step one is the most important here. And what messes people up is they forget how you even decide the direction of the electric field and how you should draw it. So I'm going to come over to a blank page to just do a quick sort of rundown of that. I'm not going to give values of charges. I'm just going to give a sense of positive or negative, because to do this first part, that's all you need. So let's say I want to know the electric field at this point right here due to a bunch of charges sitting all around it. So maybe I've got a positive charge right here, could be a positive charge over there. Maybe there's a negative charge off right here, another one up here. I'm just kind of picking stuff. And I'll number them off. 1, 2, 3, and 4. And the procedure to get your vectors for each is to pretend there's a little positive charge at the point you're interested in. There doesn't have to be, because fields exist whether there's anything around to feel them or not. It's the whole tree falls in a forest thing. Yes, there is still a field there even if nothing is around to experience it. But we use a test charge, our little pretend Q0, to measure the effects of that field. And so we'd see, first of all, that charge 1 would repel it. It would push it away. That means the field due to charge 1, E1, is away from charge 1. And away means along the line between the two. One thing that I see sometimes is people try and sketch in the entire field pattern, the field lines, and so they'll draw a bunch of arrows in all directions. And then that actually, it doesn't steer you wrong. It just kind of makes a mess of the picture, and it can mess you up when you're trying to draw the other ones. Or they'll try to get the field lines to connect between all the charges. And honestly, that's a harder problem to do than what's being asked. All right, charge 2, it would also repel a little positive charge if it were at this middle point. And so the field due to charge 2 is away. Charge 3 would attract a little positive charge at that origin. And so the field due to charge 3 is towards charge 3. And charge 4 would also attract a little positive charge at the origin. So the field due to it is towards charge 4. And now I've got 4 vectors. I can do vector addition. It is the exact same vector addition as you've ever done in my class, Physics 1, any class where you've done vector addition. So I like to do it with a table. You find your x and y components separately. And I haven't given a whole lot of information here, so maybe I can add some stuff like, I'll call this angle theta 1. I'll call this angle theta 2. And then E3 and E4 are on the axes, so we don't need angles for them. So E1, E2, E3, and E4. One thing I'll mention at this point is This is already a lot more work than just taking the numbers E1, E2, what you get by using KQ over R squared. I see this so often and it hurts so bad every time I see it. This is not how you find a net electric field because they're vectors. Direction matters. You can't just add them like that unless they happen to be along the same direction. They're very much not here. So if you see a problem where I've left you a ton of space and it's worth 14 points, the answer is not just add the numbers together like I just wrote. All right, so for E1, it points to the left and down. So it has a negative x component and a negative y component. They're equal to E1 times something, either sine or cosine. To decide which, I come over to my picture and I draw in my components. So E1 points to the left. I would have to walk to the left to get to it, and then I would have to walk downwards to get there. So that leftward component, which is E1x, is adjacent to the theta 2 angle. I'm sorry, theta, how did I keep messing this up? Theta 1. That should be theta 1 because it's for field 1, and this should be theta 2. Okay, so it's adjacent to theta 1. It's adjacent, so I would use cosine. And then the other component out over here, I have to go across to it. I have to go opposite theta 1, so I would use sine. Okay, now on to E2. To get there from the origin, I have to walk to the left, and then I have to walk upward. So it has a negative x component and a positive y. They're equal to E2 times something, either sine or cosine. In this case, E2x is adjacent to theta 2, so I'd use cosine. And E2y is opposite, so I use sine. If I gave this angle instead, those would swap roles, because then I'd get to vector E2 by walking up and then to the left. And so I would say, okay, my y component is adjacent to that angle, and then my x component is opposite. So you do have to remember the only thing that matters for deciding whether to use sine or cosine is if your component is adjacent to the angle, you use cosine. If it's opposite, you use sine. There is no x or y rule for that. E3, it's pretty easy. It points purely to the left. So there is no sine or cosine. All of it is to the left. None of it is up or down. And then for E4, none of it is to the left or right. All of it is upward. You add down your columns, and that will give you your net electric field components. But then you actually have to calculate, okay, what is E1? It's K times the size of charge 1. You've already accounted for direction, so we use absolute value to not double count direction, over R1 squared, which is how far charge 1 is from the point you're interested in. It's the distance from charge 1 to the point we're interested in. So it would be that distance right there is R1. And so on for E2, E3, E4. Once you get all that and you put it into your calculations for the net x and y components, the overall net electric field, this is the final step, is you get from Pythagorean theorem. And your angle, if you're specifying relative to the x-axis, it would be y over x. And I like to stress, do absolute values as in don't worry about the signs of these components here, because the angle that you spit out, if you do that, will always be between 0 and 90, and based on your picture, you should be able to figure out which quadrant it's in. If you don't do that, you'll get some negative angles sometimes, and it may not be as clear what that means. And half the time, it actually is the calculator screwing you over, because it's essentially assuming something that's not true. But I won't get into that, just do absolute values. The last thing I could ask about this type of question is, okay, so if I put something there, Because we said we're pretending something's at the middle. Say I actually put something there. What kind of force will it feel? So in terms of the strength of it, it's just going to be the size of the charge you decide to put there. So this is a new charge that I haven't talked about at this stage. It's maybe I bring in an electron or something, times that net electric field you just found. The direction of it would be either in the direction of the net electric field if it's a positive charge, or opposite that direction if it's negative. And so I would have to, based on my picture, sort of guess which way the net electric field points, or use my components to figure out which way it points. So I'll just go based on sort of a rough guess. So E2 was this way, E1 was this way, E3 is that way, and E4 is that way. So I can already at least guess it's going to be either in this quadrant or this quadrant. As in, I've got four quadrants. It's either in the top left or bottom left one. I would guess top left because the E2 and E1 vectors look to be about the same size, at least the way I sketched them, and that would mean their vertical components cancel, but their horizontal components add, so I get this as my E1 plus E2 vector. And then I add that to E3, so I get an even larger vector for E1 plus E2 plus E3. And finally, E4 points a little bit upwards, so I would get E1 plus E2 plus E3, and then add on that last vector, E4. So my net electric field might point something like that. If I put a positive charge at the origin, then it will feel a force in that same direction. It will feel a force this way. If I put a negative charge there, it will feel a force in the exact opposite direction. All right, I would do it for easier fields and directions than this, but that's the general idea. So field lines, just these properties. If this example makes sense to you, I think you'll be fine. Just remember that positive charges source field lines, they spray them out in all directions, and negative charges sink field lines, they're a drain for them to flow into. And so even if I don't tell you what kind of charge something is, you can figure it out just by knowing field lines point away from positive and towards negative. So if you just have the field lines, you can figure out the charges that are present. If I did something with the dipole, it would have more to do with the torque. So it would be like, what is the torque, which would be a very plug and chug kind of calculation, but more importantly, the rotation and when is torque largest and smallest. Torque is largest when the dipole is furthest away from being in alignment with the field, because that's what it tries to do over time, is rotate until it's aligned. Once it reaches that point, the torque is zero, because in that case, if we look at this picture, you've got this force pulling to the left and this force pulling to the right if this bottom left charge is negative and top right is positive. And it's going to tend to rotate the whole thing until you're in this state where the negative charge is being pulled this way, the positive charge is being pulled that way. And in that case, it's stretching the dipole, it's not rotating it anymore. So that's where the torque goes to zero, when you are in alignment. Dipole moment follows the same trend. When it's perpendicular to the field, you've got max torque, and when it's parallel, you've got zero torque. If I had stuff for rings and disks, it would just be like the pluggiest, chuggiest thing you could ever see, which is why I don't tend to ask stuff about these. I'm not going to make you rederive it. And then maybe if I want to do an extra step, it would be like, what's the net electric field due to two rings? And I want to know it here. Well, if this ring is, say, positive, and this one is negative, I'll call this ring 2, and this ring 1. The field from ring 1 points away from it because it's positive. The field from ring 2 points towards it because it's negative. So the net electric field in this picture would point to the right. And the size of it would be add the size of the positive rings field to the size of the negative rings, and you can really just add in this case. This is just regular addition because these two vectors are in the same direction as each other, and will always be for rings unless I oriented them weird, which I wouldn't do. Gauss's law. It is more conceptual stuff that gets people for this chapter, as you saw on the quiz. The calculation, I'll just jump to it, is just this. It's tedious, it's a long calculation, but it's essentially just an algorithm. It's something you can follow every time, shut your brain off a little bit, and still at least get close to the right answer. So, as long as I see the work being put in, if there's little mistakes, it's little points off. I just want to see you follow through to the end and try and evaluate this flux through each face. Just remember that it's easier to make sure your answers are right if you sketch the vector field first and guess what the flux should be through each face based on that vector field. If your calculations don't line up with that, you probably did something wrong in the calculation. Otherwise, to answer almost any concept question about Gauss's law, you just got to remember what it says, which this is the shorthand for it. Number of field lines through a surface is proportional to the charge inside the surface or inside the bag, if you want. In that case, every problem that seems like it's going to take a lot of work becomes one line. So, for instance, I have a positive charge and I've put it inside of a big shell, a big conductor of some sort. And that conductor, and let's say in this case, is neutral. All right, what is the electric field going to look like out here? Or sorry, let me say electric flux first, and then I'll say electric field. Well, the only charge I see is this one, so the flux is equal to whatever that charge is over epsilon 0. I don't even have to do anything. I don't have to think about, well, that's going to induce some negative charge on this inner surface and leave some positive on it. It doesn't matter because what's enclosed by that bag is just this charge. To get the electric field for that, that's where you say, okay, well, the field is uniform over that surface. The area vectors are always aligned with the field. So I can pull stuff out of the integral and I get E times 4 pi r squared, where that's the surface area of the big Gaussian sphere. It's equal to the charge inside over epsilon 0. So it just looks like what you'd get for a single point charge, which makes sense because the shell is effectively not doing anything. It's neutral, so why should it contribute overall to the field? Um, and there was that question on the quiz like that of like which one has a 0 flux? Well, it's the one where the charge isn't inside the bag. If there's no charge inside the bag, there's no net flux through the bag. So, when in doubt on a Gauss's law question, just write this down and think about it for a second. Don't try and start calculating.
So on earlier with the cube,
Mm-hmm.
I remember on the homework there was one where you didn't uh, do the flux for the bottom, and then on there was a question right after where you did do the flux for the bottom of the cube.
Okay.
Could you explain that for me real quick?
It didn't ask you to find it, or
Or I guess you could. It was just equal to zero, and I didn't understand why.
oh, okay. My guess for why, without exactly remembering the problem, is if we've got a cube and our electric field just grazes the cube on that side, the flux should be 0 because it's not poking in or out. Or
Uh-huh. Oh, okay.
yeah, if that's your area vector, if you want to go through the calculation, it's that E dot dA. Since they're perpendicular to each other, the dot product gives 0 over that face.
Mm-hmm.
And that's true for every little patch of that bottom face, so adding up all of them will give 0 as well.
Okay, that makes more sense.
Okay.
Thank you.
Uh-huh. You won't typically have to do calculations like we did here, or like the later ones with the charged whatevers. Um, so I more stick to the reasoning stuff. But for some of the field strengths we found, I may have you do something with that. But then it is just like a here's how you figure out the strength of that field. Now do something with it. It's not derive this from scratch for me. So for instance, for the capacitor, I could give you the plate area and I could give you the total charge on either plate. And I ask you, okay, that's going to create some kind of field, and I put, say, an electron in there. What kind of force acts on it? Well, first of all, I know it's upward, opposite the direction of the field. That also means, without me even giving it in a picture or anything, that the top plate is positive because the field lines point away from the top plate and the bottom plate is negative. And then that's another way to see that it makes sense. The electron moves towards the top plate, it's attracted to the positive charge. But to figure out the strength of the force on it, so I know the direction, what's the size? It's as before, the size of the charge, in this case the electron charge, times the strength of the field it's sitting in. In this case, that's the field of the capacitor. So that's charge density over epsilon 0. And then charge density is the charge on the plates over the area of the plates. So just to differentiate between that and the electron charge, maybe I'll call it Q plate over area, and then all divided by epsilon 0. And so depending on what you're given, you can juggle those things around in different ways and figure out what's being asked for, the field or how much charge is on the plates or whatever variant. But it's all very similar kind of calculations. I don't think I'll do anything with the charged ball. Maybe the charged shell, but again, in like the way I was talking about up here, where'd it go? Like this kind of problem, which is essentially what the last problem of the chapter is, except in that last problem, I do ask how much charge is on either face. Oh, I guess this one didn't have that saved yet. But anyway, this problem in the notes is the other kind of calculation type question I tend to ask. So this and the flux through the cube are the most common ones. So if you practice those and you kind of get the algorithm behind it, that's all it is just the same kind of calculation with slightly different numbers. Okay, so that's my little bit long-winded review. I want to get into questions that y'all have.
I uh, I have a question, and this is also in regards to the homework.
If someone can pull that up for me, I'll do the problem. I just don't remember the exact numbers. It does kind of depend on the exact layout. They always pick those carefully so that you don't end up having to do actual integration. Although there are some like that that I try to avoid. I hope I didn't mess up and give you one where you did have to do that. In the meantime, other questions?
It's just in regards to the field vector addition
Mm-hmm.
um for chapter 22. So basically, we're looking at how the the other charges are affecting our test charge and not the other way around.
Right. Yes. So that is a good point. And it is another thing I see get mixed up is let's say I have a negative charge here and negative here, positive, positive. I will see sometimes people will draw their field vector for, say, this positive charge on the left. They'll say it's away because, yeah, if there were a little positive charge here, it would repel it. You're not wrong, you're just answering the wrong question. So the question is about what would happen to a little positive charge sitting at the point we're interested in. And it's, an imaginary charge. We're pretending there's something there. It would be pushed this way by that charge to the left. It would be pushed this way by the charge beneath it. it would be attracted towards the charge above it, and it would be attracted towards the charge to the right of it. And all of those vectors are also anchored to this point rather than, say, this one where it's being attracted to the negative charge up above. I don't want to draw it like this because then I get confused when trying to add the vectors because that's never how I've drawn vectors to add them. And, same goes for you. You may draw it like that because it makes sense at the time, and then you don't know what to do with it to add it to the other vectors. And another thing on that is, okay, when we are talking about forces between charges rather than the fields that charges create, that question where it's like 2 protons and an electron, and the question is, what is, say, the force on that central proton? The proton to the left of it will repel it, and so it will push that middle proton to the right. Yes, the middle proton would push it to the left, but that's not what's being asked about. So I don't draw that because it'll just confuse me. And then similar for the electron. The middle proton will be attracted to it, so it will feel a force to the right. Yes, the electron will be attracted towards the proton as well, but I don't care. That's not what's being asked about. And so the net electric field in this case, net force on the central proton would be to the right as well, the vector addition of those. Is anybody able to get that problem? Okay, he's done the work for me. This is going to look cleaner than if I did it anyway. So, assuming you got the correct answer on this, I'd go with what Josh shared.
I got the correct answer, but I'm still like I was unclear about the bottom part for one
Okay.
of the problems.
So the bottom part is in like how you get the charge out once you know the flux, or
Yeah, or let me
the
double
bottom
check.
face is what you're saying.
Yeah, the bottom face.
Okay, let me pull this up on my phone so I can see it a little better. Okay, so the electric field is 4I hat minus 1.2 y squared plus 3.3 j hat, and it's 0.75 for the edge length. I guess does it not give the coordinates for these two sides? It must not vary over the x. Oh yeah, because it's just 4. Okay. So I would try and at least sketch the field here, and so it's going to have a positive x component at all times. It's a constant x component. For the y component, it is going to be negative. It'll point downward whether I am above or below the, it would be the xz plane, but y equals 0. So might look something like, let's see, each field will point down and to the right, but it will point further down the farther away I get from y equals 0. So at y equals 0, I will have no y component. It'll just point to the right. And it'll get shallower as I go. And then down beneath, it should do the same thing. And then get steeper as we get further away down beneath. So judging from that, the flux through the left face should be negative because the field lines are poking in on that left side. The flux through the right face should be positive. The flux through the top face should be negative because it's poking in. The flux through the bottom face is 0 because that's in that xz plane where the field only points to the right. It does not have a y component. So that's why the flux through the bottom face is 0.
Okay, that makes so much more sense. Thank you.
Mm-hmm. And then I can also say the same for the front and back faces because the field is not sticking out of the screen towards me or into the screen. It's only to the right or down. So it's not poking out through the front or through the back. And so really, I've just got those 3 faces, the left, the top, and the right face to deal with. So flux through.
Oh,
Yes.
when I did do it this way though, I got it wrong and
Okay.
it wanted me to count the bottom face for the use it. I actually had a number for the bottom face, which was weird. So I don't know.
Oh. Okay. Okay. Sorry, I forgot this piece. So I was looking at just y squared, but it'll have a value of 3.3 times negative 1.2 in that um, xz plane. So it actually will point downwards there. So we would have, it would be a positive flux through the bottom. That's my mistake.
Okay, now I get it.
Yeah.
Thank you.
Yep. Sorry about that. Okay, so we need to do left, right, top, and bottom. I'll do, you know what, I'll do the left face first. So flux through the left face, I don't want green, is integral E dot dA over the left. And that's all this stuff. Dotted with the area vector for the left face, it pokes out towards the left because it always points outward from the surface. So it is negative dA in the I hat direction because it's along the x-axis. So negative dA I hat. And j hat dot I hat is going to be 0, so all that's left is this first term. So negative 4 integral of dA over the left face. So it's negative 4 times the area of the left face, which is 0.75 squared. And that's some number. Through the right. Should be the same thing, except positive because the x component doesn't grow as we move along the x-axis. So I'm not expecting any additional flux. I'm just expecting it to be in the opposite direction through the right face. But if I go through, that's integral yada yada. And now the only difference is dotted with dA in the positive I hat direction because the area vector for the right face pokes out to the right. So that will be 4 integral over the right face dA should be 4 times 0.75 squared. Okay, flux through the top face. The area vector for the top face is going to point upwards. So it'll point in the positive y direction. So it'll be dA j hat. So all of this stuff, y squared plus 3.3 j hat dotted with dA j hat. So now the right term survives. Negative 1.2 integral of y squared plus 3.3 dA over the top face. Okay, over the top face, y does not vary. It should be always equal to 0.75 because the bottom of the cube is in the xz plane, so y equals 0. The top is at y equals 0.75. So this is integral over the top face, 0.75 squared plus 3.3 dA, which is negative 1.2 times all that stuff in parentheses, the 0.75 squared plus 3.3 times the area of the top face, which is 0.75 squared. And okay, that is going to give a negative, which is what we were thinking would happen. And then through the bottom, it should be positive because the field vectors are poking out, and that's going to show up from this last term. The area vector for the bottom face is negative dA j hat. And so for that bottom face, integral over the bottom, E dot dA is 4i minus all this stuff, but dotted with negative dA. Didn't leave myself room for that. Dotted with negative dA, j hat. And so I get a negative here, a negative there. That's a positive 1.2 integral over the bottom face. Da-da-da, dA. But on the bottom face, y is always equal to 0 because I'm in this xz plane where y is going to be equal to 0. So this is gone. It's 1.2, 3.3, and then the area of the bottom face, which is again 0.75 squared. And that's going to be a number. You add all these up, that's your total flux, and then that's equal to the charge enclosed over epsilon 0. Does all that track?
Yep, you explained it really good. Thank you.
And I think it was Douglas maybe asking at first.
Yeah, and I appreciate you explaining that, and thank you, Josh, for posting those notes in the chat, and it broadened my understanding. I accidentally combined question 2 and 3 of the homework together.
Okay.
Question 3 was a lot easier than question 2, but I got the hang of question 3, so thank you.
Okay. Yeah, and there is, let's see, two things to mention here. One is the y squared stuff. It's very easy to be like, oh crap, how am I going to do that? Because it looks like an integral, and that's where you have to just look to see, is it really changing? The other thing is, if I give you, instead of a cube, it's a box, which I think I did for that other problem in the homework. You just have to be careful about which face you're finding the area of. So in all of these, it was always the same size because it's a cube. The only thing that changes if it's a box is that last little bit, the integral of dA. If it's the front face, you're finding this area. If it's the right face, this area. If it's the top face, this area. And so the box is a little bit harder that way, but it's the same math in all other regards. Other questions?
So we can expect this kind of problem on the exam?
Yes. Look at it this way. It'll be worth a good number of points, and if you know how to do it, it's free points. Okay, any other questions? All right, well, if not, I think I've covered the main gotchas that I see. I feel like that's the big stuff that I see, is mainly the stuff I said about the electric fields, where you got to be careful about what you're looking at the direction of, and that it is vector addition, not regular addition. And I guess the big thing is, remember that potential is not on this exam. So V equals KQ over R, all that stuff we've been talking about, it's not on here. So just get that out of your mind, get the idea of adding together the potentials out of your mind for the sake of this exam, because that is the other mistake I see, is like it just gets mashed up with finding the net electric field. And I get that, but it is just sort of like you have to put a divider between what's on this exam and what we've been talking about recently. All right, y'all have a good day. I will see you on Tuesday. Email me if you have any questions in the meantime.